Oh, thanks. So let me just recap what we left off last time. Okay. The thing coming from last time was that the perfect matching on planar graphs can be computed if you have a Pfaffian orientation, and that's the case if it's a planar graph. And then we have defined what's called a match gates, which is basically a planar graph with some external nodes. And for each match gate, we define a signature, it's called, or a tensor, or a vector of values. Basically, you take a pattern of 0, 1s of external nodes, and you remove them, and you look at the graph left, and we'll see some examples in a bit, and then you think about its perfect matching value, and that's the value assigned at that entry. So that's the entry defined by the perfect matching with the pattern of the vertices removed, summing over all perfect matchings of the graph remaining of the weight of the particular perfect matching. If all the weights are 1, then it's just counting the number of perfect matchings. And then we also mentioned the last time that the perfect matching can be, counting perfect matching can be expressed in such a uniform way called the Holland problem, where you assign the exact one function at every vertex and look at edges as variables, and then you take the edge to be in or out, and for every particular pattern, locally for every vertex, exactly one is incident is the perfect matching requirement, and the sum over 0, 1s, where the zeros indicate it's not a valid matching, 1 indicate it is, becomes the number of perfect matchings. Right? So this is just a way of formalizing. It's like expressing your satisfiability problem in constraint satisfaction problem or something. You just write down a particular set of functions that will talk about this problem. And then, of course, then this really is an example of this expression, this framework of addressing counting problems, where you think about a graph, you think about a set of constraint functions sitting on the vertices, and then the edges are variables. Let's just think about 0, 1 assignments of the variables, and then you evaluate at every vertex. So here, for example, is a non-0, 1 example where if you say, I want to talk about edge coloring, okay, so you pick red or blue or green, 3 different possibilities for the edge. And then at every vertex is the constraint that Andre talked about, that the not all equal constraint. Okay, so the vertex says all the edges must be different, and that's a 0, 1 valued constraint function. And the product of that is the conjunction, in this case, of everywhere at every vertex. It looks like the edge constraint satisfaction is satisfied, that they're all different color. And you sum over all this, then it becomes the number of valid edge colorings. Right? So you can pick anything sort of you like, and pretty soon we'll see that for the idea of the holographic reduction, it really behooves us not to restrict these values to be just 0, 1s, because the true understanding comes around by looking at them as numbers. In fact, we'll come to the point where I want to argue that even unlike constraint satisfaction problem, where you have sort of a dual view of variables and the constraints, try to think about variables are another kinds of constraints, which is just saying they are all equal at this vertex or at this constraint. Okay, that's the variable. The variable has to be consistent in assigning values, that's all. Okay? And we're going to change these functions around, and you're going to see that the equality constraint is a perfectly bona fide constraint function, just like easing constraint or something. Okay? All right. So let's look at an example of something that is naturally expressible as a Holland problem and then solved in polynomial time by this method of match gates and Castellian's algorithm, even though on the surface of it may look like it would require exponential time. So the instance is your planar graph of maximum degree 3. And in fact, for this talk, let's just think of them as a regular 3 graph. So every vertex has degree 3. And you're looking for orientations. So orientation is an assignment of a direction for each edge, either this way or that way. And then at every vertex, this is called the icing model or some ice model or something. You want at every vertex so that it is not the case that everybody coming in or everybody going away. So 2 coming in, 1 coming out is okay. 1 coming in, 2 coming out is okay. But it is not okay to have everybody coming in. So I suppose these models come from Pauling's in these chemistry or physics, where you have these local ice models and you have some local constraints, and you look at the configurations as valid, and then you think about them as some sort of weight or energy, and then I'm not going to get into that. I'm really no expert in that. But let's just say I'm talking about a graph problem. Okay? So you have every local constraint to be a non or equal. So this is really a no sink, no source. If you are a graph theorist, this is just no sink, no source orientation. Okay? There's another way, purely another way of saying it. But now think in terms of the Holland problem. What you have now is that at every vertex, okay, let's say you have a degree 3 vertex, then the constraint is the not all equal. Okay, you think about sort of coming in or going away as 0 or 1, and then you're saying it's not all 0 or not all 1. Right? 0, 1, I mean, we computer scientists think about 0, 1. It's just another way of saying yes or no, in or out, up and down. It's just a spin. I mean, okay, whatever. All right. Now, what about, okay, so this is a notation that says that if I have a function that is a symmetric in the sense that the value only depends on the number of ones, okay, so another way of saying it is invariant on the permutation of the variables, it's a symmetric function, then I can specify such a function with only the value on the Hamming weight of 0, 1, 2, up to n. So n plus 1 values will specify the function. Except, unlike if it's a general case, it will be 2 to the n values will specify the truth table. Okay. So in the case of the not all equal, then you're saying if the Hamming weight is 0 and Hamming weight is 3, they are both no good. That's a 0 output. And if the Hamming weight is 1, 1 in, 2 out, or 2 in, 1 out, then it's fine. So this is just a shorthand to say here is the function. But you can also think of this as a shorthand of writing down, in this case, 2 to the 3 numbers, 3 inputs, a truth table, okay? And it will be indexed as 0, 0, 0 for the 0 value, 0, 0, 1 for the 1 value, 0, 1, 0, 0, 1, 1, 1, 0, da, 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 da. Okay, so you can write down a dimension 8 vector. And the way I'm belaboring on this sort of thing is because we are about to do arithmetical operations, linear algebraic operations on these, so far merely an assemblage of values. And we're going to think about them as truly good, honest vectors in some vector space, and we're going to transform them in this tensor way. Okay? So this is why it's also important now that we should not think about them as a Boolean, merely Boolean values of indicating true or false, but it's just numbers now. Okay, now what about the orientation? Well, there's a standard way to reduce CSP to Holland problems. So in some sense, Holland is a bit more expressive. But here's an example, basically. It take every edge, you do what's called a stretching. You replace it by a path of length 2. Okay? And then on that vertex, the new vertex on the length of path 2, then you can have a constraint on them. So you basically saying, so originally this was a variable and here are the constraints sitting on them. Okay? But now I'm going to replace this by saying here is a new variable and that f is still sitting on them, g is sitting on them, but I have an equality function on them. So this function now takes variables here and there, and ostensibly this originally was 0, 1, and ostensibly there were 4 possibilities, but it's in fact only 2 possibilities will be valid because the equality forces the both sides to be. Okay, so this is just a sleight of hand. It's trivialist gadget of yours, right? I'll write down a path of length 2. Okay. Another way, if you think in graph theoretically, this is the edge-vertex incidence graph. Okay, so it becomes a bipartite graph. On the one side is all degree 2, these are the original edges, and they are all equality of binary 2, and the other side of the original constraints. And in this bipartite view, you think of this as a constraint satisfaction problem if you like, the equalities are going to be treated soon enough as perfectly good constraint functions. And we're going to transform them like ordinary vectors. Now, in this particular example, it's not the equality. I want orientation. So on this particular example, what I have is actually the assignment of sort of this way or that way, and will be naturally represented by the following possibility of 0, 1, or 1, 0. Okay? And then I will then just do the following trick, right? Second trivialist gadget with a disequality function over here, and ostensibly you have 4 possibilities, but it's just 0, 1, 1, 0. So it's orientation. Good. So on the one side there will be vertices labeled by binary disequality functions. On the other side will be the original constraint functions, the not all equal function. But disequality on binary is also not all equal, if you will. Okay, so they're all disequalities in some sense right now. So this is the Holland view of what this no sink, no source orientation problem is. Okay, all right. So as I said, this is the edge-vertex incidence graph. And then the Holland sum can be now viewed as summing over all possible 0, 1s on half edges. So there are this 2 to the 2e terms. And for each one of those terms of 0, 1s, you're subject to the constraint that they are all satisfied. Those edge disequality are all satisfied. And those are all satisfied. And to satisfy 2 things of a constraint function as a truth table, you can write them as a tensor product of the 2 vectors. Think about tensor as a vector. Because it's say think of the 0, 1s. When you say, A00, A01, A10, A11 as a binary function. And here's another binary function, B00, B01, B10, B11. And you multiply them all out, it's 1 if and only if both are 1. That's the tensor product in the most primitive, none of this highbrow tensor algebra. Just think of the Kronecker product, right? Just multiply this with this, multiply this with this. Okay, you expand out, you have a 4-dimensional vector, tensor 4-dimensional vector, you get a 16-dimensional vector. And that 16-dimensional vector, every entry is just a 1 entry here times 1 entry there. And it's 1 if and only if both are 1, if it's a 0, 1 case. And if the weight, then it just multiplies. It's exactly what we want. Okay, so the tensor product here represents exactly the sort of, in the Boolean case, the conjunction in the CSP language is exactly what the gadget should be. Okay, so now if you write down all the constraints on the edges on one side as a tensor products, and that will give you a vector of 2 to the 2e dimension. And on the right side, you also tensor product all those constraints, and that's also giving you 2 to the 2e dimension. And then you do a dot product term by term. It is just summing over all possible 0, 1 possibilities of these half edges of potential orientation assignments, and subject to the constraint that if it is a valid constraint of orientation. Okay, first on the left side says, is it the case that you're assigning 2 different values for each edge? So it's an orientation. On the right side, it says, yeah, my thing coming, some are 0, some are 1, not all 0. Okay? And another constraint says, nope, yeah, I'm fine. And if any one of those is violated, then the whole product becomes 0, so that becomes a 0 term into this dot product. So this whole long dot product is merely a restatement of the original problem, trying out all possibilities. So far I've done nothing. Okay, this is absolutely nothing, totally trivial. I'm just re-saying 1 is a 1 is a 1 is 1. That's all. Okay? Maybe 1 plus 1 is 2. All right, good. All right, so we are going to assign these functions and think about them as a shorthand of a dimension 8 vector here, and there will be tensor product all together. And now I'm going to ask you to think of this dot product as a long vector, and the computation is unthinkable, right? This is like 2 to the 2e term computation, and it's no better than just enumerating all possibilities at this point. However, I'm going to ask you now to think about what's called a holographic transformation. Okay? I'm going to ask you to change your vector by this. Okay? So in particular, I told you this was really an 8-dimensional vector. And this 8-dimensional vector, I can multiply the h by a tensor power 3. Okay? And effectively, graphically, what we are doing is to change the function on this f by the new function, which is you do an h here and h here and h here. And if you did this transformation, you get a new a-dimensional vector. And in fact, I computed this for you. And here now algebra comes in nicely. You don't want to really write down an a-dimensional vector and matrix and multiply. You can do this, this thing, which I guess in the more abstract definition of tensor product and tensors, this is the definitional thing that you are multilinear, you can distribute of products. Okay? So the tensor of a matrix multiplied by a tensor of vectors is the tensor of the product. So A times B tensor something is A tensor times B tensor that distributes. So that's in the more advanced treatment of tensor product. This is the definitional thing. Okay, but you can directly verify this is the case. All right, but now I am writing this thing. Remember, what is this? It's an a-dimensional vector which has a 0 in the 0, 0, 0 place and a 0 at the 1, 1, 1 place and a 1 in the 6 other places, right? That's the vector. That's the a-dimensional vector. Merely so far is just like truth table of saying true, false. But I'm thinking of them as numbers now. And I'm expressing it in the following way. See, this guy gives me an a-dimensional vector of all ones. And this guy gives me an a-dimensional vector of a single one at the 0, 0, 0 place. And this gives me an a-dimensional vector at the 1, 1, 1 place. So I'm taking all ones, subtracting two ones at the beginning and the end. I get exactly the vector I want. This is a reassemblage of what originally was a Boolean value of 0, 1, but now I'm writing it as if they're perfect, good, honest numbers and doing arithmetic on them. And the tensor product does the distribution. So what is h times the 1, 1, 1? Well, that's like you add the two columns together. So it gives 2, 0, right? 2, 0 tensor 8, 3 gives you an 8-dimensional vector of 8, 0, 0, 0, 0, 0, 0, 0, okay? And then you, hocus pocus, you get this number, okay? So this is obvious. I mean, now you can see sort of some strange things happening. We are breaking apart an originally a perfect good logical design from Intel that says true, false, da, 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 da. And now I'm assembling it into sort of superpositions, if you like, quantum. Superpositions of these other funny pieces which don't really exist in reality. And then my computation somehow distributes and gives me the computation I want. Okay? And similarly, I can do the other way. And this, I'm doing the inverse transformation. Actually, it should be the inverse and transpose, but this is a symmetric, so it's fine. And in fact, it's almost its own inverse up to a factor of 2, right? Quantum people would insist writing this as a 1 over square root of 2 so that this is orthogonal. But to us, constant factors don't matter. So all right, so you get this, okay? So you get this number. Now, what's the big deal? I mean, why isn't 0, 1, 1, 0 more beautiful than 6, 0, minus 2, 0? What have you done? What you have done is the following. It turns out that these guys are match gauge signatures. Okay? And if you can transform to something by this holographic transformation, that the Holland value, the dot product, is unchanged. Because what you really have done is you have a dot product, and you're multiplying some big matrices. So you have this dot product, and here, and I'm multiplying by an H and H inverse to its high power. And then distributes the tensor product all over. So the value is unchanged. But then I can imagine that as if the local function is not the f, but this 6, 0, minus 2, 0. As now you can see that the minus do come in, and that this is important, that I allow myself this freedom to do this business. Okay? All right, and these two turns out that are match gates. So here is a proof by example, or the demonstration by construction. Right? So I'm claiming this is a match gate. And if you take away any pattern of these 3 vertices, 8 possibilities, really, but by symmetry, really only 4 possibilities. By parity, is only 2 possibilities. Okay, so you count the even, you can't take all 3 out because it's even all left, right? So you can take 1 or 3 out. Okay, if you take all 3 out, sorry, what am I saying? Take 1. Yeah? Take how many? I can't count. There's 6 of them. So I have to take 0 or take 2 out. Thank you very much. Even odd gets me. Okay, so you take 2 out. Let's say you take 1 and a 2 out. It's symmetric. So you take the 1 or 2 out. Then this must be matched here, and this must be matched there. Okay, and this is just giving you a scalar 6. So this is a minus 2. Okay, and if you take none out, then this must match, this must match, this must match. You get 6 because of 6. Okay, so this is just an example of a match gate. Okay, it's the perfect matching after you remove some external nodes and you look at the perfect matching and you sum over. In general, of course, there will be exponentially many possible things inside. You have to sum and you have to add and subtract and so on and so forth. But here's a particularly simple example, just to show that this is a match gate signature. All right, so now imagine that I'm plugging in this thing by that. Okay, and then the 0, 1 business, and I'm going to plug in something here too as a match gate. And then I'm thinking 0, 1 as taking the perfect matching in, taking this edge in the perfect matching or not. And then summing over all possible such patterns. And given the external pattern of taking or not taking, and then think about all possible internal perfect matchings. It takes a moment to think, but I think you can convince yourself after a few seconds that this final thing really is the counting of the total perfect matchings of the entire graph once I've replaced these guys by the match gates. So this is sort of, in a nutshell, what holographic algorithm 2 reduction to match gates is all about. I have the original constraint somehow sitting somewhere, and that expresses the problem. I want to solve it. It's a Holland problem, let's say. And then I will try to replace it after a holographic transformation by some other constraint functions so that they are actually now match gate signatures. And if they are match gate signatures, I can use Castellian's algorithm to find. So it is still at this point this long exponential dot product, but that's not how I'm going to compute this. All right? This quantity represents in another realization as the perfect matching of the graph. So I'm going to do it the Castellian way. Okay, so that's the sort of, in a nutshell, what this thing is. And here's another match case that does this. Okay, so then it becomes sort of a, I should say that Les Valling introduced this, and there were some magical problems that he said he could solve, like, counting 3 mod. Let me not even get into it. So some very strange problem that you really wouldn't think about. So monotone, read twice, counting of number of satisfactions mod 7. So you want the answer to be, the number of satisfactions to be either 0 or 1 or 2 or 3 or 4 or 5 or 6. And there's a companion problem that says if it's just mod 2, let's say it's even or odd. And it turns out that the mod 2 is already hard, okay, NP hard. And it turns out that mod 7 in this case is solvable in polynomial time. So there are these sort of pretty strange problems that were solved in polynomial time. And then it behooves us, in the classification perspective, what are solvable? I mean, okay, so you can be very ambitious and say, I want to solve a Sharpe-Hart problem. That's what I want in polynomial time. So what I instead say is that let's try to really carve out exactly what these things can do. And so one step forward is to say, for example, characterize all the signatures that were realizable by match gates that are symmetric. And we'll see in a bit that we have characterizations for all signatures that are representable by match gates. And they turned out to be related to something called the spinor variety. And they are captured by this class of equations called the match gates identities. I'll come to that. Okay, so shifting gear, I want to talk about the sort of another class of holographic algorithms that have nothing to do with reduction to the Castellians now. Okay, in particular, they will work not just for planar graphs, but for any graphs. So recall that I'm writing a symmetric signature in this way, the Hamming weight of Hamming weight 0 value, Hamming weight 1 value, and so on. Okay? And look at this guy. Okay? So it's a perfectly good 0, 1. You can't complain about 0, 1, even though I argue that you shouldn't even complain about non-0, 1. But being such 0, 1, you really can complain, right? It says, I just don't like you to have exactly 1. Okay? 0 is okay, 2 is okay, 3 is okay, but 1 is not okay. All right? Now, this, by some perspective, it's a Fibonacci sequence, right? This is equal to these two sum, and this is equal to these two sum. So now, it turns out that we can define such a signature as a Fibonacci gate if it satisfies the Fibonacci recurrence. Okay? So I can write down Fibonacci sequence anywhere, any long line. And then these will be functions you can put on a graph, and then you can say, well, what is the Holland problem? What's the value on that? Okay? It turns out that these are computable in polynomial time. So I think it was a bit of a surprise, at least to us. But more importantly, actually, this actually represents a class of problems that are tractable. And not only that, on top of that, it represents a basic ingredient in the classification. So this represents one big class of the tractable class of the classification dichotomy theorem, where you say it's either this or this or this. And this is one of the things that are transformable to this by holographic transformations. So this took us actually several years to evolve into this perspective where we're going to get to a point where even the expression, so we start off with holographic transformations as a tool to do some algorithms, very fantastic algorithms. And then we come to a point where we use the holographic reductions as a tool to prove hardness, as a reduction method of hardness. But then it comes to a point where we're actually going to express the statement of what is tractable, what is not, in terms of holographic transformations. Okay. So this is the statement that this thing is, if you put Fibonacci there in any graph, it doesn't have to be planar now, this is transformed. And I don't want to get into the details, and the details are not that difficult, but basically the proof that it's tractable, one way of proving it is to say that if I have two Fibonacci signatures, I merge two edges of the external edge, and I get a new signature of, if there was 4 and 3, I get a 5, okay, arity 5 variables. And I prove that this is also Fibonacci. So it's not, I think, obvious from the face of it, but it is. Okay, you can just check it is so. And once you have that, then there's another operation that you do the self loop of two external nodes. And then you can say that you can just sort of imagine that you have a signature grid with Fibonacci's everywhere. And you initially you cut off every connections, and they're all Fibonacci's individually. And you merge one piece after another, and you kept saying it's Fibonacci, it's Fibonacci. In the end, it's just a Fibonacci, and that's a number, right? Okay, so this is like the brain-dead algorithm, right? Okay. And the same argument actually works for this so-called generalized Fibonacci, that if you have a parameter, arbitrary parameter sitting here, same argument works. And here's the definition, what's called the generalized equality, which is you put any number here when it's all 0. Any number else doesn't have to be the same, doesn't be 0, 1. It could be 0 even, any number, 1, whatever. And if they are anything disequal, then you output 0. It requires them to be equal, or the input, but output may be something else. And it turns out that if you take this class, these are the things that satisfy the Fibonacci recurrence, with one exception, with one or two exceptions. Okay? And you add this guy in, which is not expressible this way, then they are sort of if you take the view of group actions, then you can argue that they are the same orbit on the orthogonal group. But basically, they are all the same in this holographic transformation thing. Okay? So here's the theorem, says that anything in this is equivalent to the following, that there exists an orthogonal that goes to here, or there's orthogonal to the original Fibonacci, or there's an orthogonal to anything in there. Under orthogonal, there's a single orbit. And this, interestingly, is not. Even though my tractability argument works for all. Okay? But this, in a deeper understanding of this class of signatures, this is actually different. This is what's called a vanishing. It's a different type. Okay, so there are some characterizations of Fibonacci gates and what can be transformed. But what is, in fact, interesting to us was that it turns out that the Fibonacci's characterize what is this class called Holland star, where I think we actually had this name before, the conservative wing of the community came. We were liberal. We didn't call it conservative. But anyway, so we called it the Holland star. Okay, it just says that you're throwing all the unarrays you like. Turns out that these unarrays, well, unarrays are Fibonacci. Okay. Okay. Let me bring some other sort of basic ideas. A signature is called a degenerate if it is a tensor product of unary ones. And in fact, this is sort of the reason, one of the reasons why unarrays are being singled out in a very, very special way, because they are very weak. Okay? If a signature is degenerate, then basically what this signature is saying is that my value doesn't really depend on all three. Oh, it depends on all three. But my value with respect to your contribution is already determined by what your value is. And I can split this into sort of three unary functions, each one of them only looking at the input respectively. It's a degenerate, that's why. Okay, it's degenerate. And if it's a binary function that's degenerate, then it's exactly the same as the 2x2 matrix, or k by k matrix if it's a domain k. Then the rank is 1, so you can decompose into a outer product of one vector with another. And so therefore, it sort of splinters at this point. Okay, so if you're having degenerate ones, it's tractable. And then now we define what's called a product type. Okay. And all of this definition will lead to the claim that you have a class of these problems, of CSP, Holland, and you want to say what are tractable. And here are the classes. Product type, and we'll see the affine type, the vanishing type, and so on and so forth. Okay. So here's the product type, very simple. A function is expressible as equalities and generalized equalities and disequalities and tensor products of these things and degenerate ones and so on. Okay, so these are called a product type. Okay, so it turns out that Fibonacci basically captures the product type. Okay, so in the conservative star liberal world, Holland star of a set of constraint functions is either polynomial time computable or sharply hard. And it is polynomial time if and only if it is of this following type. Okay, it's arrayed at most 2, which then you can do what's called a trace by matrix product. Or it is under a suitable transformation, it becomes the product type. So this is not the original way we found or proved these theorems, but this is like the transformational perspective of what, conceptually what it is. Okay? Or there's one extra thing, which is this sort of the 2i type Fibonacci, which is actually vanishing. Okay, so this is the first classification. Oh, let me mention that someone mentioned, several of you told me that you didn't get a chance to copy down my book address. It's a dichotomy book.pdf on my website. And this is chapter 1. Okay, so this is like where I start the theory using this. And it turns out that the ability to construct unary ones is very important in the later work. And that's why this is chapter 1. Okay, let me move on to CSP. Everybody already knows the definition. You have a set of constraint functions, and now you really think sort of in a separate way. You have variables here and the constraints there, and the constraint apply to the variables. And then you sum over the variables and multiply over the constraints. Now I want to introduce another class called affine. Okay? And here's the definition. You have some constant. You have a support, a characteristic 0, 1 function on an affine linear subspace. And then you have I, the square root of 1, minus 1, to a exponent of 0, 1 indication functions summed up. And each one of them is the 0, 1 indication functions of an affine linear subspace. Okay, so this is what this is. There's an alternative way of writing this, And I think that's sort of a nice indication that some class is nice if you have actually more than one way of looking at it. Here's another way of looking at it. It turns out that the thing up there can be viewed as a quadratic polynomial in the xi's, with this one additional constraint that the cross terms must have even coefficient. Okay. And then these are if and only if. You can't do with it. This is not just a short. This is one of the nice things about dichotomy theorem is that once you prove that, you can say it's not that we didn't do it right. The theorem says this is the right definition. Okay. Okay. Now, to get some concrete understanding of this class, let's think about the symmetric functions of this class. And they turn out to be expressible in these three families. And I'm now already taking the liberty of writing them as tensor product sums. So you should think about this as a vector of 2 to the k long, as a truth table of a function, but I'm expressing it as sums of tensors. And so they came ready to be transformed by holographic transformations. Okay? Now, I hope nobody will complain that I have complex numbers around. And you will see that, in fact, that they are really essential. Okay? For example, I think David, who was it, talked about, or was she talked about, that this, for the graph homomorphism case, okay, if it's 0, 0, 0, 1, 1, 0, they are all 1, and 1, 1 is negative 1. That counts the number of odd induced subgraphs. Perfectly 0, 1 question. Okay? Is expressible in this family by choosing 1 plus I as the lambda, and in the third family. Now, if you think a little deeper, in fact, you should not really be surprised why these sort of perfectly good, honest 0, 1 kind of things will give rise to complex numbers, because these are the eigenvalues. Okay? It is really the eigenvalues in the analysis of these problems that give rise inexorably to these complex numbers must make their appearance. So I'm going to make no apologies henceforth that things could possibly be complex numbers. So if you expand them out, as you see, for example, this binary function, if you truncate off of 1, 1, 1 minus 1, is this Adama function, whose graph homomorphism status was open for quite some time. And this family are all tractable. This is all in the affine family. Okay. And then comes the next theorem for the dichotomy for the CSP, and this extends the Holland star. It says, and the proof of this uses the Holland star, to say that we have two classes, basically, of tractable here. It's either in affine or in product type. Let me caution, this statement is to say that it's either entirely in affine or entirely in P. It's not that it's contained in affine union P. They cannot mix. And this is, in fact, one of the substantial amount of proofs when in later, here too, but in later dichotomies where you want to argue that there are no mixing. Unlike the Markov chains, you like mixing. Here you say there are no mixing. So big chapters, big sections of long papers were devoted to proving no mixing. Okay. I should mention that there's quite a bit of a pre-work that builds up into this, and many of the people in this audience had contributed to this.
Can you remind me for a second what P is?
Product type.
Okay.
These are the holographic transformations of Fibonacci with one additional vanishing type. So I mentioned some of these. So far I've been really focused on just Boolean domain, but let me mention that she already talked about the graph homomorphism in the general domain, higher domain, that's substantially more work. And the constraint satisfaction for general domain, Andre also mentioned. So the graph homomorphism partition function comes from here. And if you're interested here, you should be able to copy this fast because I'm not going to be able to have time to write down here. But it's collected here, quite a good collection number of papers that he or his co-authors have written. 30, 40 papers over. Okay, so this is the dichotomy theorem starting with Dyer and Greenhills for the 0-1 case. And she talked about this really beautiful extension by Bulatov and Groh on the non-negative case. It's particularly nice because it's sort of very much usable. Okay, you can use that as a criteria to prove other things. And then there was a paper by, let me get this right, I think Goldberg, Groh, Jeremy, 30, on the real. The real is a real progress because there are the cancellations. And the cancellation is the source of tractable problems. And because the presence of these beautiful tractable things, to prove that nothing else becomes much harder. Okay. So this is the thing maybe she will talk about. I'll skip this. Again, there's a long list of beautiful work before that. So let me mention a dichotomy we know about Holland problems, which is a bit harder because it really, a dichotomy of this would imply the CSP. And furthermore, trying to classify for planar problems, like going back to the Castellians type. And as I perhaps mentioned last time already, the upshot that we seem to come to understand and not fully proved is that for Holland problems, it turns out that this holographic reduction to the match gates is not universal, but for CSP type, for the planar, it is. And it's ironic because the Castellian was really designed for this, the matching problem. It's the Holland type, it's not the CSP. So I think it still requires some understanding there. So here's a notion of called a C, class C transformable, that there is some transformation that makes the equalities on the edge to the C and the constraints into the C as well. So this is like just what you think should be the contravariant transformation, the covariant transformation. Now I'm speaking in tons, in tensor. So here's a theorem that says you're given a symmetric complex valued functions on Boolean variables arbitrarily, disregarding planarity. This problem is either sharply hard or it satisfies the following, in which case it would be in polynomial time. Okay, so this is the dichotomy. And here are the few classes. There's the affine type, the affine transformable, the product type, the P transformable, the sort of degenerate arity at most 2 type, that's the trace computation. I think yesterday there was a talk in physics where you assume some random model where you say that it's likely that the local thing is a tree, and then things are easy to compute. That's basically what this is. It's acyclic, you can just compute in this way. And then there are 2 classes that involve vanishing. Okay, and I think I will actually skip this part because it will take a little doing to really define what these things are. Quickly, a signature is vanishing if you put it in a signature grid, and if the signature grid only use these vanishing ones of the same type, this type is either plus or minus type, then the value will be 0. And this phenomenon seems to only occur if you have complex numbers. Like 1i, your dot itself becomes 0. Okay. Now you say, well, okay, so who cares about these things? Well, it turns out that they actually interact with other things, so that when you are not just vanishing, but there are other things, it would produce non-vanishing values, but the classification would require the understanding of the vanish. So if you are entirely vanishing without any part here, yes, you are tractable, and the value is a simple 0. But that's you know. Okay, you say you don't care about that, but you must, because together with others will produce non-zero ones. And in order to understand what is tractable, you must understand all that. This is, again, my philosophical reversion to the claim that these things self-justify their own existence by the theorem. Let me mention this match gates identity. So remember, you are given a match gates and you assign the match gates signature, okay? And then the claim is that it satisfies the match gates identity. And in fact, there's a separate part of the proof that says that if you do satisfy all these, then you are the match gates. So this is a complete characterization of it. And the match gates identity says that if you take any two patterns of 0, 1, that's the number of external nodes, you do the XOR, which have a bunch of zeros. That's the place where the alpha, beta are different. And then you sum this funny-looking thing of the sum of alternating sum of these values where you flip the bits where they differ. Okay, so you have alpha pattern, beta pattern, and you start to flip both in alpha and in beta of the places where they differ. And you multiply them and you alternate sum and you get this and you get 0. This is the claim. It must be so. And the original thing was for an array 4. In a very concrete case, you have 4 external things, and you prove that 16 values of this thing satisfy this. That's valid. And we have arrived at the proof, and eventually we thought to be a better proof because they were really complicated proofs. But I would really like to show you a new proof by Mark Jerome, who was reading this and said, oh, I have a better proof. Of course he does. So I'll show you the better proof. So what are we supposed to prove? We have two patterns, and they are differ on these guys. Now let's take two perfect matchings, because it's the perfect matching summing over all these guys is going to be the signature entry for which you're multiplying together, and then you assemblage again, and then right? Inside here are the sums, the weighted sums of the perfect matchings of these guys. So let's take one here, take one there. Okay? What did I tell you the last time that if you have two perfect matchings, what do you do? The first thing you do. That's a little quiz here for the students, of course. You superimpose. Yeah, that's the only thing you do. So once you superimpose, you get a bunch of, these are perfect matchings, on the graph where you already removed some external nodes, so they're not in the same graph. So in this case, you have cycles, even length, and paths. But both cycles and paths are alternating. So one edge is in M, one edge is in M prime, and so on and so forth. Okay? But the E sub P sub I, so this is the 0, 0, 0, 0, 1 at the P sub I place, and 1, 1, 1, 1, 1. So the XOR says I'm flipping the PI bit of alpha. That's where alpha and beta are different. So that external nodes of PI, one of them is in the removal pattern, one of them is out. I don't know which one, but it's definitely one is in, one out. Okay? So therefore, that must lead a path, not a cycle. A path that starts with an edge that's either in M or M prime. It's on exactly one of them. Then followed by the other kind, and then alternate. And will end up somewhere. It cannot end up with a cycle. So it has to end up somewhere, and that's the P sub j where they differ, where the alpha and beta differ. So this, if you take two perfect matchings, it will define this alternating path to a P sub j somewhere. Okay? And now if you think about this as a planar thing, then this P sub I leads to a P sub j. The external differences of P sub k's must in even number, because they are also leading paths of alternating paths that cannot cross this. So it has to go over there. So therefore the j and I must be of an opposite parity. Okay? So this sets up a one-to-one correspondence from this to that. So from some I, any I will give you a j, some j, and this is an involution. If you start with the flipped matching pair, you come back, you get to the exactly original pair. So this sets up with a one-to-one correspondence with a total, and you can check the weights match and so on. And this will set up, this is exactly the negative signed sum term. This is the positive sum term. Okay, go back to this. Okay, so the even odd just alternate. Let me mention that a beautiful theorem due to Hung and Tyson that says that if I now talk about CSP with planar restriction, and the functions are complex value and symmetric, then it is now either in affine or in product or in this transformed match gates. Okay, so this is the sort of the statement giving weight to the claim that this is universal for the things that are tractable in polynomial time over planar, but generally not. Because this captures things that were not. This captures things that are tractable in the non-planar case. Now let me skip the action part. Shifting gear for 5 some minutes to talk about a technique that is very often used in these reductions. We start with the Tott polynomial. Okay. If you've never seen a Tott polynomial, I think it's impossible to grasp this at this point. But it's some polynomial in 2 variables, x, y, in the graph. Okay? And J.J. Vertigan-Welsh has a theorem that says that other than these values, or this parabola, it is Sharpe-Hart. Otherwise, it's polynomial. And over the planar ones, you have one additional parabola that is polynomial. Here's the definition of what's called the medial graph. So you're given such a graph, a planar graph, you take every edge to be a new vertex, and if they share the same face, you put an edge in it. Okay? And this, now you take the black parts out, this is called the medial graph. And one more definition, an Eulerian orientation. So you come to a vertex, Eulerian sort of path, you come in, come out, come in, come out, you always can just come around, right? So it's not a surprise to say that I want the number of things in to be equal to the number of things out. That's obviously a necessary condition, but it's also sufficient in Eulerian. Okay, so here's a theorem due to Las Vegas that says that the Tott polynomial evaluated at this particular pair of points, 3, 3, is the sum over the medial graph of saddle points, where saddle points are things the orientation is in, out, summing over orientations, and at saddle points you put this factor 2. Okay, so, and since this is hard, this is hard. And this is really a Holland problem in its perfectly good, honest way. You have orientations per edges, we already did this. And then what's the constraint at the vertex? Oh, I should say that the medial graphs are always 4 regular. Okay? The planar graph, you know. Okay? So you're talking about vertices that are degree 4, and you want in, out, something like that. Okay? And a signature for that is obviously a arity4 function that says 0, 0, 0, 1, 1, 0, okay, whatever the value is, okay? And that turns out to be, for this particular thing, in order to capture the saddle, is this thing, okay? 0, 0, 0, 1, 1, 0, 1, 1 coming from one direction, 1, 0, 0, 0, 1, 1, 0, 1, 1 coming from the other direction. So I'm drawing it this way. You can imagine that the sort of 4 wires coming in the orientation, and it gives you the value. All the non-zero values happen on the weight 2 part. Now, it turns out that I can do this transformation, but so far it's, of course, these 0, 1 values and perfectly fine. You're saying, wait, I like to do a complex transformation. Okay, so here's the I sitting in there. And it turns out that the Z transformation will transform this disequality into equality. Okay. And under the Z transformation, this signature I just told you becomes this. So this is my, if you like quantum, you can think of this as the superposition of the external 0011 world with the inside of the 0110 world. But whatever, it's a 16 numbers. It's just the truth table of this function. Okay, and this is the function after the transformation under Z. Okay, now what about the Eulerian orientation? Well, this says that it's a 2 in, 2 out. Everything else is 0. Under the Z transformation, it becomes 3, 0, 1, 0, 3. Again, magic of holographic transformation. Pure computation, right? So what we would like is to reduce, the tut to the Eulerian. And if I do this gadget, this is a slightly more advanced gadget than the single edge gadget. You put the Eulerian everywhere. That gives you a new arity 4 function. Okay? And you can compute this. This is this. Once you have this, then you would like to you can reduce the tut to this. That's what you like. And that will prove the hardness of the Eulerian orientation. You go from the tut to this. On the holographic transformation, go to the Eulerian orientation. So you have these two matrices. You like to try to interpolate this by that. And what you do is you design now a sequence of gadgets. You replace the one you have by sort of a sequence of things that you would like to reduce from. And once you do that, you might sort of impressionistically believe me, if you don't quite work out the detail, that if this guy is 0, 0, 0, 1, 1, 0, 1, 1 coming out, and here's 0, 0, 0, 1, 1, 0, 1, 1 coming out, and this is 0, 0, 0, 1, 1, it's like a matrix product in order to somehow get the signature of this. Okay? You're writing over sum over all possible 0, 0, 0, 1, 1, 0, 1, 1, and that's the matrix of 4 by 4 times 4 by 4. And so if you think that way, then the iteration gives you iterative multiplication, and if you have iterative multiplication, then eigenvalues is natural, right? And this is why complex numbers sort of, this is very natural. Okay, but in this case, actually, we can do a direct arithmetic, and you sum the value you want, stratified according to how many times this occurs, how many times these two types occur, and how many times this occur. And once you have that, you can express your value in this way, where Cij is the sum of all other things all over the place, with the 3 to the j many times. And the other term, once you replace the s times, you get this. And by prime factorization, these guys are going to be different from this. And so you would get is a linear system with these as coefficients. And this coefficient matrices, this coefficient matrix is a Vandermonde that is non-degenerate, and you can just argue for every different I, j, k, and j prime, k prime tuple, they will be not the same because of prime factorization. And so therefore you can solve for these. Once you solve for the Cij, you can go back to solve for this. That's the reduction. Okay? And I think I'll stop here. Thank you very much.
Any questions? So, do you think this project is ever going to end?
Well, there's a lot of things that's still unknown. Maybe I should mention a few things that are unknown, right? So, for example, for the Holland dichotomy, we have basically only done the symmetric functions. Furthermore, it is basically almost entirely on the Boolean domain. So if you have higher domain, we have only one result. There's the planar thing, which again, for the Holland, we have no idea. For symmetric, we have, but asymmetric functions we don't.
So, I mean, you mentioned the result on the planar CSP.
Yeah.
That's a special kind of planar CSP, isn't it?
What do you mean by special?
Well, I mean, it's basically a Boolean.
Yes, only on Boolean. Yeah. So beyond Boolean and planar, it's virtually no.
So you don't see any hope of breakthrough in the near future on this?
Define hope and near. And these are terms that are very crucial. I don't know. I would, encourage students or anyone who's interested, look into the things and see there are lots of things that are unknown. For example, we are currently trying to get what's called a 6-vertex model. And this is statistical physics people like this. You have a matrix like this. And the support is on weight 2. So 2 in, 2 out. And I guess the physics motivation was that you have grids and you have functions sitting on them and you have orientations. And every time some physics reason that it has to be 2 in, 2 out. And then you have a value here. And you multiply them. That would, of course, fall into the Holland dichotomy if we have a full Holland. But this is not symmetric now. No. But even for that, it seems quite challenging. And there are new tractable problems in the planar case that are not by holographic transformation to the match gates, which is a new thing we really don't have a lot of understanding.
So
what are they by? If they're not by match gates, what are the new things?
So it's a global realization that you view it in a different way, and then you identify cycles as new variables, and then you do holographic transformation on that graph. So but you have to argue very carefully that you didn't break planarity, and then indeed there's this sort of a cycle thing that comes out. Because they can do things like that. And still oscillate.
Any other questions? No? Okay, well let's break for lunch.
Thank you.